Hi everybody. This is just a short video to elaborate a little bit on what we did in lecture 27. I am a firm believer in the idea that when you take the effort to solve a problem, then once you get your answer, you ought to try to stand back for a moment and try to squeeze it, you might think, and get every drop of insight that you can out of the work that you have done. And so that's the spirit behind this video. I want to look at what we have done in lecture 27 and try to get some extra insight out of it. And I think that you'll find this interesting. At least I do. I think it's really pretty neat. And fortunately, this will be very short, but I think you'll find it interesting. And also, the first few minutes of this video could be helpful to you for the final exam. Now, I'm going to then go on to a more advanced topic, which will be entirely for fun, which would probably not help you on the final exam, but still, I hope that you'll find this interesting. But anyway, this is just a brief review now. In lecture 26, what we were dealing with is the problem described up here at the top. What we wanted to do was to design a state machine that would detect the sequence 0, 1. In other words, if the last input was 0 and the present input was 1, then the machine should output a 1. But for any other sequence, it should output a 0. So this is a detector. It detects this sequence 0, 1. And in test 26, we found out that if we were going to implement that using D flip-flops, then and maybe let me back up a little bit. What we decided to do in solving this problem was to define 4 states. And the 4 states were that the last 2 inputs were the sequence 0, 0. S1 was the last 2 inputs were 0, 1. S2 was 1, 0. And S3 was 1, 1. And so for that kind of description of this problem, we decided that we would have 2 flip-flops, one of whose output would be A, and the other one, the output would be B. And when A was 0 and B was 0, then that would be S0, and so on. And we found out that in what our test 26 was about was if we used D flip-flops for A and B, then the excitation table should look like this. That was what we determined in test 26. And then in test 27, what we did was we looked at, I don't want to go too far here. Okay, so in test 27, what we did was we took, this is what we did right here. We took that excitation table from test 26. This is the same excitation table here. And then we found minimal sum expressions for dA, dB, and Z. And what we found out was that dA is simply equal to B, dB is equal to X, and Z is equal to X B prime. Now, you might have thought when you did test 27 that the purpose of that was simply to give you a little bit of extra practice with doing cardinal maps. But in a real life problem, what we did in test 27 is a very practical thing, because what we did was to find efficient ways of realizing the excitations dA and dB, and we also obtained a way of realizing the output Z as well. And like I say, these are efficient, these are minimal sum representations. So minimal sum ways of realizing those two excitations in the output. So you might say, well, so what? Well, the importance of that is that now we have a very efficient circuit or a very efficient state machine for actually implementing this problem. And the state machine looks like this. Here's your flip-flop that has output of A. It's a D flip-flop. Here's the D flip-flop that outputs B. And let's look at this very carefully and see that all the circuitry is right. Now remember, okay, we said that Z is equal to X B prime. Well, here's the flip-flop for B, and here's the B output, so this would be the B prime output. And so we have B prime ANDed with X. So indeed, this looks like the correct circuit, the correct connections for Z. And dA is just equal to B, and dB is equal to X. So let's see about that. Here, dB, the input to the D flip-flop is indeed equal to X, and dA is indeed equal to B. So what we're saying is that the circuitry needed to build this detector is just this simple. And actually, we have achieved something else, because when you look at that, you can easily see that there's no point in the D flip-flop for A. I mean, this is not doing anything at all because it's producing an A output that is never used. So actually, we could X that out and just have this as our detector. All it consists of is this D flip-flop for B and this AND gate. And our claim is that this would detect the sequence 0, 1. So let's investigate this even a little further and see how it would work. Okay? So what I've done here, and let me erase some of this because I don't want to give it all away. Okay. Now, as you have seen on our previous problems, for these flip-flops, we generally need to have an initial state. So I'm going to say that this flip-flop right here is initially in the state B equals 0. And I'm also going to say that I have an input sequence 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. And I want to see if this state machine here is going to correctly give me a 1 every time the present input and the previous input form the sequence 0, 1 and a 0 at all other times. Okay, that's the idea. And so let's just look and see. Okay, now keep in mind that B is the output of a D flip-flop. And we know that the way a D flip-flop works is that the next value of B is equal to the present value of D. So you get D, and there's, that's the name of this is D stands for delay. So the next B will be D. But D in this case is equal to X. So the next value of B will be X. So if X is equal to 0 here, you should think of this as time is getting larger in this direction, okay? So if the present value of X is 0 here, then that means the next value of B will be 0. And likewise, if the value of X then is 1, that means the next value of B will be 1. And now if the present value of X is 0, then the next value of B will be 0. And you can see that in each case, we just go up diagonally like this. And so, what we get then is 0, 1, 1, 0, 0, 1, 0. And again, you can see how there's this diagonal sort of connection here. 0 goes to 0, 1 goes to 1, 0 to 0, 0 to 0, 1 to 1, 1 to 1, 0 to 0, 0 to 0, 1 to 1, 0 to 0. And again, the reason for that is that the way a D flip-flop works is that the next value of the output is equal to the present value of the input. Okay. Oh, and by the way, one more thing I want to point out to you. Now, this X sequence that I have right here, this was chosen pretty much randomly. But there is one very important thing about it. As I say, we want to test this circuitry to make sure that it gives us an output of 1 whenever the current input and the immediately previous input or immediately preceding input form the sequence 0, 1 and gives us a 0 at all other times. Well, this sequence will allow us to determine that, because notice that we have all possible pairs present. Here we have 0, 1, and we have 1, 0, we have 0, 0, and we have 1, 1. So all possible pairs are there, and we'll get to see if this thing really works the way it should. Now, we're almost ready to do this problem, but we have to decide now, what is Z going to be? And remember, Z is going to be equal to B prime ANDed with X. Okay, B prime ANDed with X. So let's fill in this Z sequence. Well, one thing you can say immediately is that since Z is equal to B prime ANDed with X, whenever X is 0, since 0 ANDed with anything is 0, if X is 0, then Z is 0. So for all the cases where X is 0, we can go ahead and put in 0. Okay. Now, for the rest of these, let's see what we should have. B prime X here, okay, B is 0, so B prime will be 1, and 1 ANDed with 1 is 1. Okay, likewise again, B prime X will be 1 ANDed with 1, which is 1. Here, B prime X, okay, 1 prime is 0, and 0 ANDed with 1 is 0. And then finally, B prime X is 1 ANDed with 1, which is 1. And now, lo and behold, you look at this and you see that it is acting perfectly, because our outputs are always 0, except when the present input and the immediately preceding input have are the sequence 0, 1. So here we have a 0, 1 giving us a 1. Here we have 0, 1 giving us a 1, and here we have 0, 1 giving us a 1. But in all other cases, the output is 0. Now, to me, that's just really interesting. It's really gratifying to see how that all worked and came together to give us this really simple circuit. And I think personally that another nice thing about it is how we see how the minimization process, it really does have a point. You see that it helped us to have a simple circuit, and it helped us to see that we could get rid of this. And just think, if you were in the business of building something like this, well, if you can get rid of unnecessary circuitry, that's going to help you to have more profit. So this to me is just really interesting, and I hope that you enjoy it. And frankly, I'll go ahead and say now, if you want to quit the video at this point, that's fine, because I will say that what we've just done is probably the only part of this video that would really help you for the final exam. But if you want to hang on for just 5 more minutes, then I'll show you something else that's interesting. Okay, so we can still get a little more insight in the following way. You might be wondering about this unnecessary part of the circuit. You might be thinking, well, why did that happen? Is there any way we could have seen that earlier? And the answer is yes. Okay? And so let me explain a little bit about this. The reason that we had something extra or redundant is a word you'll frequently see in situations like this. The reason that we had something redundant in here is that back in lecture 26, when we defined those 4 states, 0, 0, 0, 1, 1, 0, and 1, 1, when we did that, well, to be honest, we really didn't need 4 states. We could have gotten by with just 2 states, which means that we only need 1 flip-flop. So how could we have detected that? Well, let's just spend just a moment and I'll introduce a new idea to you. Now this idea is something called redundancy tables. And I'm certainly not going to try to give you a complete description of this topic, but I just want to show you how it will work in this case. Okay, so let's remember exactly what we had. Okay, we had A and B, 0, 0, 0, 1, 1, 0, 1, 1, and this was S0, this was S1, S2, S3, and now let's say A plus, B plus, for x equals 0 and x equals 1, and then z for x equals 0 and x equals 1. Okay. Now, remember that that really the way that we defined S0, S1, S2, and S3 means that, like for instance, let's say S0. 0, 0 means that 0, 0 is the last 2 inputs we've had. S1, 0, 1 means that 0, 1 are the last 2 inputs we've had. In other words, you might say that A represents the input we had 2 steps ago, and B is the input we had just 1 step ago, the very most recent input. So, and X here in these columns, X represents the present input. And so let's see how this goes. If the last input that we had was B, which is 0, and our present input is 0, meaning we're here in this column, then our next state will be 0, 0. That does not match the sequence that we want, so we output a 0. On the other hand, if our last input was 1, and our present input, again, is 0, then we will be in the state 1, 0. And again, that doesn't match what we want, so we output a 0. And then you can see next one is if our last input was 0 and present input is X, then we have 0, 0, and that output is 0. And then finally, if our last input was 1 and our present input is 0, then that means we're in 1, 0, and output is 0. Okay. And now let's okay. Now let's go down the X equals 1 column. If the last input was 0 and the present input is 1, then we go to the 0, 1 state, and that is the desired sequence, so we'll output a 1 here. If our last input was 1 and present input is 1, then we have 1, 1. That does not match our desired sequence, so we output a 0. And here, if our last input was 0 and our present input is 1, then we have 0, 1, and that does match it. And finally, if our last input was 1 and our present input is 1, we go to 1, 1, and output 0. So this is the transition table for this problem. But let me put this, we also have the very closely related state table. And so we have, current state, next state, X equals 0, X equals 1, output Z, X equals 0, X equals 1. And so we have S0, S1, S2, S3, and then we can see that we have S0, S1, S0, S1, this should be 1, 0 is S2 here. Okay, so S2 and S2 here. Okay, and then 0, 1 is S1, and 1, 1 is S3, and then S1, S3. And then here we have 0, 0, 0, 0, 1, 0, 1, 0. So here is our state table. Now look at that state table for a moment. I don't think it's a great leap of imagination to just think about drawing a line right through the middle of this and observing how much the lower half of that state table looks like the upper half. And that's a real strong hint that we have more states here than we really need, that in fact we have redundancy. And so the way that a redundancy table goes is this. And once again, I emphasize now, you don't need this for the final exam. This topic will not be on the final exam. So again, if this is not of interest to you, don't worry about it. Just stop the video. But I have just a couple of more minutes to go. So the way that a redundancy table goes is this. You'll say S0, S1, S2, S3. S0, S1, S2, S3. And then we'll draw boxes like this. And each one of these boxes represents a question, basically. It's saying, could the state to the left be equal to the state below? So for instance, for this box, this one represents the question, could state 1, which is the one to the left, be equal to state 0, which is the one below? Could S1 be equal to S0? And the answer to that is no, because if we look up here at S0 and S1, we see it from these first two lines that if you're in S0 and the input is 1, you'll output a 1. But if you're in S1 and the input is 1, the output will be 0. So S0 and S1 do not react in the same way, or when the system is in state 0, S0 or S1, it doesn't react in the same way to an input of x equals 1, and so therefore those two states cannot possibly be the same, and so we'll put an x there. Those two states cannot be the same. Now what about S2 and S0? Well, if you look at S2 and S0, just looking at the outputs now, the outputs look exactly the same. And now if we look at the transitions, well, those look the same as well, because if you're in S2 and the input is 0, you will go to S0. Or if you're in S0 and the input is 0, you'll go to S0. See, I'm comparing this and this. They're exactly the same. And likewise, this and this are the same. So it looks very much like S2 and S0 could be the same. So I don't put any mark here at all. I just leave that blank. Now go down to the next one, S3 and S0. Could they be the same? And the answer is certainly no. They couldn't. S3 and S0 could not be the same, because when the system is in state S0 and the input is 1, it outputs a 1. But if the circuit is in state S3 and the input is 1, it will output a 0. So these two, S3 and S0, could not be the same. Now let's start going down the second column. Okay, could S2 be equal to S1? Okay, let's see, S2 and S1. No, they certainly could not be the same, because, well, you can see right here, the outputs don't match. So S2 and S1 could not be the same. Okay, what about S3 and S1? Well, the outputs match, and also the transitions match as well. S2, S2, S3, S3. So we will leave this one right here, we'll leave that blank, because those could be equal. And then finally we'll ask, could S2 and S3 be the same? S2 and S3, that's this one and this one, and you can see the outputs are different, so we can immediately say no, they cannot be the same. Now typically in a redundancy table, in those boxes that represent possibilities, the two that are blank, you'll have to write down some conditions. But in this case, we didn't have to write down any conditions at all. Everything is just sort of automatically satisfied, and I don't want to go into that detail anymore, because again, this is not going to be our final exam. I just want you to get the basic idea. So when we finish the redundancy table, and we have not reached any contradictions at all to the possibilities that S0 is equal to S2 and S1 is equal to S3. So instead of using 4 states with this problem, we really only need 2. And you think about it, and it makes sense. S0, remember, that's the state 0, 0, and S1 is the state 0, 1. Well, so in other words, the last 2 inputs, S0 is the state where the last 2 inputs were 0, 0. S1 is the state where the last 2 inputs were 0, 1. But really, you don't need to have any more states than that. I mean, really, what you need to think of is to define maybe 2 different states. We'll call it alpha, means last input was 0. That's really what S0 means, because the one prior to that is not really important anymore once you get your present input. No, it's just like what I was saying is, like up here, when we were determining everything here and everything here, you might remember we were always looking at B. We never did look at A at all. A is not important. And that's why we really don't need 4 states. We just need 2 states. So alpha is the last input was 0. Beta is last input was 1. And that's really all you need, is just 2 states. And so that means that it's sufficient just to have like, if you want to call it B, like I want to make sure you see what I'm saying here. We can have B 0 or 1, and this is the alpha state, and this is the beta state, and then X 0, 1, Z for X equals 0, X equals 1, and this should not have that messed up here. B plus X equals 0, X equals 1. Now remember, if you look at it this way, B is just the most recent input. So if X is equal to 0, then the next value of B is 0. If X is equal to, and that's true in either case, and in either case, if X is equal to 1, then that means the most recent value of X is 1. So that's easy. But notice that in the first row, we would have the sequence 0, 0. So we have put 0 here, 1 there, 0 here, because that's 1, 0 for the two for the previous input and the present input, and this is 1, 1, so we'd have 0 here. We make sure that that's clear. This right here is 0, because it means the previous input was 0 and the present input was 0, and 0, 0 is not desired, so that's 0. This would be 0, 1, so we get 1 here. This 1, 0 gives us 0, and finally 1, 1 gives us 0. And so this right here would be a minimal transition table for us. And I guess as long as I've come this far, I might as well go ahead and finish it. So you can see here that, well, let me take a quick break here. Okay, so let's think again that we're going to have a D flip-flop. B is the output of a D output, excuse me, a D flip-flop. So we have B is 0, 1, and we're going to have DB X equals 0, X equals 1, Z X equals 0, X equals 1, And of course, you can read dB directly from here because, as we've already said, the next value of B is equal to dB. So we have 0, 0, and 1, 1. And here, we have 0, 1, 0, 0. And you can see then if you do the Carnot map for dB, well, really, to be honest, I think you can just see by looking at it that dB is equal to X. And then for Z, that one probably we shouldn't. I mean, see, I'm just saying here. And maybe I'm going a little too fast, so let me make sure. So dB is just a function of X and B. 0, 1, 0, 1. And when X is equal to 0, dB is 0. And when X is equal to 1, dB is 1. And so we conclude then from this is, again, this is the Carnot map for dB. We conclude dB equals X. On the other hand, if we do the Carnot map for Z, and again, we have X and B, 0, 1, 0, 1. And so when X is equal to 0, Z is equal to 0, but when X is equal to 1 and B is equal to 0, we have 1, but when X is equal to 1 and B is equal to 1, we have 0. And so you can see that that Carnot map is Z equals B prime X. And so now if we do the if we make the circuit, okay, here's our D flip-flop. We have dB is the input, and here's the B output and the B prime output. And we see dB is equal to X. And we see that Z is equal to B prime X. And of course, you notice right away that that is exactly what we had up here after we took out the flip-flop for A. So to answer the question that might have occurred to you, again, remember what I said was, it might occur to you, well, would there have been any way to have foreseen this redundancy? And the answer is yes. If we had taken the states that we had and formed, look at, we had our state table here, and then if we had used a formed a redundancy table, we would have seen that actually we were using too many states, and that S2 was really the same state as S0, S3 was really the same state as S1, and so really we could get by with just the two states, S0 and S1, instead of using four states. So that's how a redundancy table can help you to minimize the number of states. But again, that's a topic that you don't need to know for the final exam. I thought it might just be interesting to you. But if you're still watching this video, then I'll just say I hope I hope this is interesting to you, and particularly everything up here in everything up here, this and everything above it is material that could be of help to you. Oh, and also this part here, I'm sorry, that part too could be of interest. We have not done this kind of thing in class yet, but we will be doing it very, very soon, where we look at the output sequence of a synchronous state machine in response to some input sequence. And this was actually, to be honest, this case was more difficult, at least in my opinion, more difficult than most of the other cases we'll look at. So anyway, that was it for just a little bit of enrichment. So I think now we've squeezed everything we can out of this, and I hope it was of some interest to you. So thanks for your attention, and good luck.